Here is a real fraud pattern. Someone gets hold of a card number and they don't spend big immediately because that gets declined and investigated. They run a tiny charge first, a couple of rand, somewhere forgettable, just to see whether the card is live. If it goes through, they hit it hard within a minute, small, then large, in a short window. As a human, you can describe that in one sentence. The question for this episode is how you say it to a machine in a way that another engineer can still read in 6 months and an analyst can extend without you. This is Flink's CEP pattern API, and I want you to notice what it looks like. It reads like the sentence I just said. Begin with a transaction under 50, follow it with 1 over 5,000. Within 60 seconds, that is the rule. The engine handles the hard parts, keeping partial matches in state as events stream past, discarding the ones that time out, and emitting only the sequences that complete. Notice there is no loop, no timestamp arithmetic, no if last transaction and current transaction and time difference. You describe the shape of the fraud, and the pattern matcher goes and finds it. That example uses 3 of the pattern vocabulary's building blocks, and it is worth knowing the difference. Next means strictly the very next event for that card, with nothing in between. Followed by means eventually, allowing other events to happen in the middle, which is usually what you want for real behavior, because a fraudster's transactions are mixed in with the cardholders. Then there are quantifiers, times, 1 or more, optional. That is how you say 3 declines in a row rather than just 1. And every pattern needs a within, a time constraint, because without it, the engine would hold partial matches forever, waiting for a second half that is never coming. That is not a stylistic choice. It is what stops your state growing without bound. Once a pattern matches, the shape of the rest is always the same. The matcher emits a match, carrying the events that caused it. You turn that into an alert with enough context to be actionable, which means the card, the pattern name, and the transactions themselves, because an analyst will absolutely ask which charges tripped this. Then that alert drives a mitigation action. What matters architecturally is that these are separate stages. The pattern doesn't know how a card gets frozen. The action doesn't know why it was asked. You can add a rule without touching the mitigation path, and you can change how you freeze a card without reopening a single rule. So why go to this trouble instead of writing the logic by hand? Because of what happens on month 6, hand-rolled rules turn into one function that everyone is scared of, where the fraud logic and the state management and the time arithmetic are tangled together, and adding a rule means understanding all of it. Declarative patterns stay separate. Each is a small object you can name, test on a fixed set of events, and reason about alone. That gets you 2 things that matter more than elegance. Patterns become data, so they can live in config and change without a deploy. And the person who actually knows what fraud looks like, the analyst, can read them and eventually write them without going through you. We can now detect the pattern while it is happening. But detection you cannot act on is just a very fast way of documenting a loss. Next episode, read this as the hot state and decision store, and freezing a compromised card inside the latency budget before the transaction clears. See you there.